Well, this week I thought we would shift away from talking about stuff on Earth. Thought it might be fun to shift away and begin to think about how about elsewhere. So, believe it or not, what we're going to do this week is we're going to tackle life in the universe, life in our solar system, and we're going to make connections between why we're alive all the way to our cell phones, and they're all connected to stars. So a lot of scientists typically believe that there is life elsewhere in the universe. And when you begin to think about the sheer volume of numbers, it's likely that there is life out there someplace. Is the universe is big, and even though there may not be that many habitable planets in our neighborhood, somewhere else in the universe there might be. The challenge, as we're going to see, is that the distances are also extremely vast, and it will take a very long time to get there. So an entire civilization could pop up, evolve, and fade away, and we never know that they existed because we just can't get there. Distances are just so big. And we'll see that when we get to relativity and talk about how we might be able to solve that problem. So we're going to tackle some of the things that we're going to need to know. So why here? Why Earth? What makes Earth special? And so why did life pop up here on Earth and not other places? Right? And why did it evolve? What do you need to have that to happen? What makes our moon so important for life here on Earth? It turns out that it's very, very important. And then how are we going to find it elsewhere? What are we going to look for? So we're going to examine how NASA uses satellites to be able to identify planets because we now have a lot of potential planets that might be similar to Earth. And then how are we changing conditions to make life feasible here on Earth? So let's talk about life formation on Earth. Where did it come from? And how did we get from point A to point B, given that at some point in our past, Earth was nothing more than a big ball of dust and gas? One of the first things that you need in any place for life to evolve, you're going to need someplace stable, right? If it's not stable, you're going to run into some serious glitches in terms of the ability for evolution to take its course. And this is, of course, going on the assumption that evolution is the driving mechanism through which life would evolve on other planets, which we have no reason to believe that it isn't. And just judging by Earth, because that is our currently our only data sample where advanced intelligent life exists, is it does seem to require billions of years, right? The Earth is about 5 billion years old, just judging by carbon dating and roughly the spectrum from the sun. And we only popped up really on the planet, you know, within the last 10,000 years. And so it took a while to get to humans. So you need something to be able to sustain that. You also need to have something that will be stable enough such that you'll be able to survive the rising luminosity of a star. And that's true of all kind of main sequence stars, which is like the sun. Sun's a pretty average star. And that over time, the sun gets brighter. And it has gotten brighter because it gets bigger. And so a bigger surface area means more light coming off of it. And we'll see what happens later with the Earth and the sun. And you might need something called plate tectonics, which you might have explored if you took Living Earth 1. And what that does is that helps to cycle and pull in and out carbon dioxide throughout the atmosphere. And it gives you a regulation mechanism through which the Earth can release carbon dioxide into the atmosphere, which is very useful because if we've seen before that if you don't have carbon dioxide in the atmosphere, most planets are actually really cold unless you're really close to the sun. Then you have to be exactly right or else you might be too hot. So let's get to this moon. So why is the moon so important? Earth is actually kind of unusual in planets is the size of the moon relative to the size of the Earth is quite significant. The moon is only 1/4 the size of the Earth, but compared to every other planet in the solar system, the moon is gigantic in terms of a satellite orbiting another planet. Mars has a couple, but they're captured asteroids. The moons of Jupiter are very small in relation to the size of Jupiter, just like for Saturn, and the other planets in the solar system are the same way. The only exception to that is Chiron, the moon for Pluto, and that's a real exception because they're roughly about the same size, so they actually orbit a center of mass that's somewhere in the middle of the two of them, so it doesn't really count. But we also know that the moon is one of the reasons why we have tides, because the gravitational effect of the moon pulls ocean water, and that might have been critical for having life transition from oceans to land, as we know that life most likely started in the oceans. The other thing that is very important, we're going to see here why, is it reduces the rotational spin of the planet. Is one of the questions that you often ask if you're going to be a future elementary educator is, do we see the same side of the moon? The answer is yes, we always see the same side of the moon because it is gravitationally locked to us, because the Earth's gravity has slowed down the moon's spin. Now, the moon spins once on its axis every 30 days, or roughly once a month. That's why we can see exactly the same side of the moon, because its rotation and revolution periods are exactly the same. And so you can test that out yourself by just holding a ball and having it spin around. You see that the ball that orbits around the center object will always face that center object if it's moving at the same rotational speed as its revolution speed. Now let's see what would happen. So here we've got a little video, and I might have to make this guy a little bit bigger so we can see it. Okay. And I'm going to adjust our screen here. And now, oops, play. So what you're looking at here is the rotational speed of Earth in relation to Jupiter. Jupiter spins once on its axis about every, whoops, sorry about that, once every 10 hours. Earth is once every 24 hours. Now, way long ago, that the Earth was spinning once on its axis about every 6 hours, which meant that a day of light was 3 hours and night was 3 hours. So that's a lot faster. Why this matters is when you look at Jupiter, it's got all these stripes and it's got that massive red spot. That's a reflection of the fact that the planet is spinning so fast, so you have some massive winds. So if the Earth was spinning at 6 hours, that would be dragging the atmosphere along with it, and that would cause constant winds. That would be much, much stronger than what we have today. That would make it much harder for life to evolve on a planet, because you would have constant winds anywhere from 100 to 200 miles an hour consistently at different points on the planet. But we don't, right? And so we're able to survive on the planet. Right? Isn't that a fairly remarkable difference in speed? The reason why we have slowed down is because the moon's gravitational force has been acting as a brake on the Earth's spin. So without the moon, you would be spinning a lot faster. Okay. Now let's go back to our other view here. Move this back over here. All right. So what would happen if it didn't exist? Well, we wouldn't have the winery Valerie the Moon, because we wouldn't have a moon. Right? That alone itself could be sad. We'd have no moonlight dinners, so that might pose some problems if we actually wanted to have the human race continue. It would also be depressing in school because we wouldn't have any eclipses, right? Because they're very exciting. And we just talked about that the day would still be 6 hours long, which would be problematic. We'd have very few mountains because the wind would cause the erosion of the mountains to go by very quickly. We'd have very small tides, and those would mostly be due to the sun. And really important here is that the moon also stabilizes the Earth's tilt at this 20 to 25 degree angle. That's very important because of the seasons. If we didn't have the moon, our planet would be a little bit more wobbly, and we would have much greater seasonal variations based upon the angle of the tilt. As right now, we tend to be within 1 degree or so, or 23.5 degrees, but the planet does wobble as it rotates and revolves, and so that's going to change the seasonal aspects of it on our planet. And that is what would happen if our moon did not exist. So, the other thing that we have to think about when we're thinking about keeping life on a planet is it warm? Is it warm enough to hold liquid water in particular? At least again, with our big data sample of 1 for the planet Earth, is we're pretty certain that life evolved from water, and water is critical for sustaining life. And so we need to have roughly the right temperature so that we can have liquid water, which is a fairly narrow range when we think about the entire temperature spectrum. So that means it needs to be absorbing the right amount of light from the star that it is orbiting. And we kind of solve that with the net logo activity of the Daisy World activity, where you have to keep the white and black flowers alive. Is it's entirely possible to kill a planet if you don't absorb or reflect enough heat back, right? And what we're looking for is we're looking for planets that are within this right area, independent of what their atmosphere might consist of and other variables, because right now that stuff is hard to detect, but we can figure out how far a planet is away from the sun. And if it's in something called the habitable zone, that's where we expect it to be, roughly in the area where there's likely to have liquid water on its surface. But again, that's a rough guide because we don't know what the atmospheric composition of these planets are, because our technology hasn't quite evolved to that point yet. Now, in the next little section, we're going to explore this habitable zone in a little bit more detail.